This example problem deals with conservation of momentum. So I have a simple drawing here, some ice as a single line, a sled, and we've got 8 kilograms of ice above the sled. The sled has 9 kilograms for its mass, and right now it's moving at 3 meters per second off to the right in the frame of reference of the ice, or somebody on the shore watching. This 8 kilograms of ice is going to drop straight down, vertically down, and land on the sled and stay on the sled. We want to calculate the velocity of the system, which would be the sled plus the ice, velocity of the system, after the collision occurs. So let's go a little further with our understanding here. Summarize the data. 9 kilogram sled moving to the right at 3 meters per second. The ice we're working on has no friction between the sled and the ice, so it's not going to affect the motion, no friction there. The 8 kilogram of ice has no horizontal velocity. It's strictly a vertical velocity, and the ice stays there, so it's going to change the mass of the system. How can we calculate the velocity? Well, can we use the principle of conservation momentum? Is momentum constant during this process, before and after? The answer is yes, because there's no friction between the sled and the ice. There's no external force that acts on this system in the horizontal direction. We hear a loud noise when the ice hits the sled, but that's vertical, and we're doing this problem in the horizontal direction to conserve momentum. There is no external force in the horizontal direction acting on the sled. Momentum is conserved, and that's going to allow us to do this calculation. So we have vertical motion for the 8 kilograms of ice. Its velocity horizontal is 0. The sled has a horizontal velocity of 3 meters per second. So calculating momentum before the collision, there are 2 parts to the system. There's the sled, and there's the ice that's dropping. The sled has this momentum, mass times velocity. The falling ice has this momentum, mass times 0 for its velocity, so we have simply 27 kilogram meters per second for momentum before the collision takes place. After the collision, there's one object. It has a mass of 9 plus 8. The falling ice has stayed on the sled, and it has the velocity we're trying to find, v. Using conservation momentum allows us to create an equation. The momentum before the event takes place equals the momentum after the event takes place. And I've simplified 9 plus 8 is 17 kilograms. So we're trying to find the v. Pull out your calculators. Hopefully you come up with 1.588 meters per second. I tend to keep 4 digits in intermediate results, but if this was our final answer, I'd round to 3. 1.59 meters per second is the speed of the sled measured in the frame of reference of the ice. What about kinetic energy? We conserve momentum. Is kinetic energy conserved? This is an inelastic collision. I'd remind you that the ice is sticking to the sled. Kinetic energy is 1/2 mv squared, 1/2 mass times v squared. Before the collision, only the sled contributes to kinetic energy. 1/2 times 9 times 3 meters per second, we square the velocity. So we have 40.5 joules of kinetic energy before the collision is kinetic energy of the sled. The ice is also moving, falling down, and it has a kinetic energy 1/2 mv squared of 102 joules. And I'd remind you, kinetic energy is a scalar. Kinetic energy does not have direction. We have 2 pieces in our system here, the sled and the ice. They both have kinetic energy. After the collision, there's one object, 17 kilograms. The previous slide, its velocity 1.588 meters per second. We have to square its velocity. And you can see kinetic energy has dropped a lot. Before we had 40 plus 102. Now we only have 21 joules of kinetic energy. Again, kinetic energy is not conserved in inelastic collision, so this is not a surprise. Well, if you'd like to see other physics and astronomy videos, short lectures, and step-by-step solutions to problems, I have a simple website, gpclements.com. My YouTube videos are listed there. And this annotation list, there's a title of the video, and there's a direct link into YouTube to play the video. You don't have to search YouTube for my videos. All the links are available to get there quickly. The annotation tells you how many minutes the video takes up and describes the video. All the content on this website is free. You're not allowed to resell it, but it's free to use. You do not give your name or your email address or any other information to the website, and the website does not put cookies on your computer. So please keep working sample problems in physics. Ask your instructor if you have questions.